Hello everyone, I am here to present my final term project for EE278, that is performance evaluation of FPGA based and GPU based block matching algorithm. My project partner is Aayush Modani and we are doing it in the guidance of Dr. Chang Chu. We have used Altera Quartus 13.0, QSys tool by Altera and then Neos 2 SBT for Eclipse. We also use the DE1 board which contains the Cyclone 2 FPGA by Altera, and for GPU we have used NVIDIA GeForce GT640 and also the OpenCV library. So we'll be evaluating the performances of the block matching algorithm on the FPGA as well as the GPU, and we'll compare both the metrics. So this is the OpenCV code that I am showing you right now, and initially what we know about FPGA and GPU architecture is that FPGA has a lot of basic blocks, and the most basic element of an FPGA are logic elements, and FPGAs are basically highly reprogrammable and configurable, and they contain a basic element called as CRAM, which can be programmed with user logic. And we are also analyzing the GPU architecture. So what GPUs have is they run through parallel threads, so they basically implement multi-thread level processing. So in GPU there are parallel threads which runs in parallel, and our graphic card has 1024 threads per block. So these threads are controlled by thread execution control unit, and we are using texture memory to read our images because texture memories are local to the thread processors, thereby acting as cache and reducing the latency. So the OpenCV code present here right now, it'll just take you to the design flow of OpenCV. So what we are doing right now is we are reading the image over here through IM read and displaying it through IM show. And first we read the image with the IM read command, and the size of the image that we read is 256 by 256, and then this is a colored image, so we are using CVT color to convert that image to a grayscale image. After the image has been converted to a grayscale image, we need to display it to a matrix format, like convert all the pixel values into a matrix format. So for that, these are the functions that I've used. So this is the declaration in the mat format, which is the data type for OpenCV, and so this is the previous frame and the current frame since we are showing motion estimation. So this is just building the file. So this is just the make file for converting the RGB to grayscale so that we get a grayscale image out of the colored one. Okay, so the file's done. We just make it. Let's run the make command, and now I'll run the display image file that we had, the CPP program. So I've used here is a Pokemon image, one of my favorite cartoon characters from childhood. So this is the current image in RGB format. This is the converted one to the grayscale. This is the previous frame in RGB and the previous frame in grayscale. So this shows that the function successfully converts the RGB to the grayscale, and all these images are 256 by 256 pixels. Now for block matching, we use the SAD algorithm, that is sum of absolute differences. So this is the make file for SAD values, which will show you the motion from the previous to the current frame. So again, build that file and then run the make command So these are the SAD values that are displayed, all the motion vectors, and you can also see the performance metric over there, that is 0.67687866 seconds, and that was the image that we saw. You can probably just run it once again just to have a look at that. Yeah, so these are the motion vectors you see. So you see arrows pointing in certain directions for showing the motion. Okay, so there you see arrows pointing in the direction of motion from the previous to the current frame. So that is okay. So let me now show you the GPU code. The general flow of CUDA programming is that there is a host, which is the CPU, and the device, which is the GPU in our case. So we use NVIDIA GeForce GT640. So what happens is the host invokes the GPU, and we use NVIDIA's CUDA compiler to compile our CUDA code. So I'll walk you through the CUDA flow now. And for this codes and for this material, we have used many websites to learn how exactly is CUDA implemented. And we are using CUDA 6.5, and the GPU, as I told you, is GeForce GT640. So I'll show you some sample code to understand how it works. And sample code is an 8x8 matrix multiplication. So in this code, we are allocating memory on the host for 3 matrices. But the thing to notice here is that we are allocating the memory for matrix. So hence the elements are stored in a linear manner. You can see that. Then what we do is we initialize the matrices on a host and then allocate memory on the device using CUDA memory allocate function, that is CUDA malloc. So after that, once the memory allocation is done, we are creating a variable thread block and a grid of type dim3 in CUDA. So that is a data type, you can say, in CUDA. Then we copy matrices from the host to the device using the CUDA memory copy function. So that copies the matrices from the CPU to the GPU, that is from the host to the device. And then we call the GPU kernel. So what the GPU kernel does is it performs multiplications parallelly with 8 parallel threads. So this is like, you can say, thread level parallelism implemented over here, and that's what the basic operation of GPU is. So now it runs 8 parallel threads because that is the size of the matrices over here, and if we try to manipulate the matrix size, you will get similar number of threads correspondingly. So now I'll run the CUDA code. So this is the compilation using the nvcc command. We have to create an object for that. It's taking a bit time, but we'll be through. Okay, that's done. Okay, so these are the values. So you can see row 1, column 2, all the it's the multiplication is done basically, and you can see the values displayed properly. So that is the flow for the GPU code we did. Okay, so now we'll go through the CUDA SAD code. So what I showed you earlier was the OpenCV flow for SAD, that is sum of absolute differences, an algorithm for block matching. So now this is the similar one implemented in CUDA. Okay, so in this code you can see that initially we have declared the width and height of the images, and the block width and the block height, and the grid for the search window. So that allows you to move a block in a particular search window and then then actually implement motion estimation. So then we are storing the current and the previous frame in a 2D array. The reason for this is we cannot allocate a 2D memory in the CPU. So basically what we are uh, doing it over here is we are storing that all the pixel values in an array. So for that we have used functions such as CUDA malloc, CUDA malloc pitch. So that is a memory allocation function in CUDA, which helped us to allocate the width and the height in bytes of a linear memory in a device, and thus in that case return a device pointer to the allocated memory. So this is the ampersand d, you can say, is the device pointer, and d underscore current is the device pointer for the current frame. So you can address it with the ampersand sign. And the next function we have used is the CUDA bind texture. So we bind the byte size of the memory area pointed by the device pointer, which is d underscore curr, to the texture reference in this case, which is text underscore curr. Then we've used CUDA memcopy 2D, so which is the memcopy function for a 2D array. This copies the matrix by the memory area pointed by the source to the memory area pointed by the destination. So that is, you can see that clearly in the code. So the same flow is followed for the previous frame as well, and after this we just invoke the GPU kernel, which performs calculation for SAD using parallel threads. We'll run the code, and you can see that there will be some values popping out. Okay, this is the creation of the CUDA object, and you can ignore the warnings for now. So like it's just warnings for some variables. That is okay. And so this is so you can see that I just run the code, and you can see all the SAD values over here using the CUDA code. So, and also in this case, as I showed you in the OpenCV, we had calculated a performance metric. So similarly we are doing it for a CUDA code. So we have calculated the performance metrics for a block matching through the GPU, for which we have created two variables, that is start and stop, of the type CUDA event. So they can record like start time and stop time, and just so we can estimate the performance of the code. And thus in this case, through the CUDA event elapsed time function, you can see there is one more function over there. Okay, you can see that CUDA event elapsed time, we have calculated the difference between the start and stop. So we get when exactly is our execution starting and stop. And through all the performance metrics that I just showed you, we can conclude that the GPU executes and performs these operations faster than the CPU. And so hope you guys enjoyed this little demo from us, and thank you so much for watching.